Hello, welcome to lesson 27. In this lesson, we're going to cover one-sided Chebyshev as well as some conditional expectation. So recall the one-sided Chebyshev inequality. We assume the mean of our random variable is 0 and the variance is finite. Then the probability that x is greater than or equal to a is less than or equal to sigma squared over a squared plus sigma squared for a greater than 0. Let's take a look at a numerical example. If a collection of beehives produces on average 100 pounds of honey per year, with variance 400, find an upper bound for the probability that next year's production exceeds 120. So the mean or expected value is 100. The variance is 400. So we have to shift over to a mean of 0. So the probability that x is greater than or equal to 120, we're going to subtract 100 from this inequality to shift this mean to 0. So this is equivalent to the probability that x minus 100 is greater than or equal to 120 minus 100, which is the probability that x minus 100 is greater than or equal to 20. The expected value of after this shift is going to be 0. The expected value of x minus 100 is the e of x minus e of 100. E of 100 is itself 100. We know e of x was 100. Difference is 0. So we've shifted it over to fit the necessary assumption that the mean is 0. Now, what is the variance here after the shift? The variance actually stays the same. The variance of x minus 100 is the same as the variance of x. Shifting does not affect the variance. It does not affect the shape or spread in the distribution. So we formally define y to be this shift, x minus 100. Its expected value is 0. Variance is the same as the original 400. So now we're ready to go. We want the probability that y is greater than or equal to 20, which is going to be less than or equal to variance 400 over 20 squared plus 400, which is 400 over 800, or 1/2. So this probability is less than or equal to 50%. So this is using one-sided Chebyshev. If instead we use Markov, we get a weaker result. So we use Markov here with the original variable x here. It's definitely non-negative, so we're okay here. So what's the probability that x is greater than or equal to, this should be 120. What's the probability x is greater than or equal to 120? It's bounded. It's less than or equal to e of x over a, which is 100 over 120.80. So Markov's inequality tells us that this probability is at most 80%. Chebyshev's one-sided tells us it's at most 50%. So it's a little bit stronger result there from Chebyshev. So again, Chebyshev tells us more. It's telling us that the answer is less than or equal to 1/2 versus less than or equal to 80%. So both give us an upper bound, but Chebyshev gives us a sharper, better upper bound, gives us more information. All right, up next, conditional expectation. So recall, regular expectation for a fair six-sided die, the expected value of a single roll is 3.5. What's the expected value if we're told that the roll is an even number? We want the expected value of x given y. X is the face value, and the condition here is that we have an even number. So expected value of x given y is summation x times p of x given y. So the given information here is that we have an even. So we want the expected value of x given an even number was rolled. So it's the sum of each x value times the conditional probability. So it's 1 times the probability of 1 given even, plus 2 times the probability of 2 given even, all the way up to 6. Now, if the roll is even, it's impossible to get an odd number. So all the odd values are going to drop out, and we're left with just the even cases. So it's 2 times the probability of 2 given even. The probability of a 2, knowing the roll is even, it's only 3 even numbers, so it's 1 out of 3. Same thing for the conditional for the 4 and the 6. They're all 1/3. And so this ends up being an expected value of 4. So we're expecting the face value to be 4, which should make sense because we're basically left with 2, 4, and 6 to choose from. All right, slightly different question here. X is the number of rolls until the first 2 appears. What's the expected value here for the number of rolls to get to a 2? So it's summation x times p of x. What would it take for x to be 1? We'd have to get the 2 on the first roll 1/6. What would it take for a 2? It means that we need 2 trials. The first time we avoid getting the 2, so 5 out of 6, and then we get it 1/6. Then the case of 3, taking 3 rolls, we'd have to miss on the first 2, 5 out of 6 apiece, and then get the correct value, get the 2 on the third roll, 1/6. And so if we factor out here, we can factor out 1/6, we get something that's almost not quite geometric, but we can convert it into geometric by multiplying this sum by the common ratio value, the R value, 5/6. So we do 5/6 times S. Now notice here, I left this 1/6 out front here and not part of the definition of S. We will have to get that, although it does end up popping out immediately here. So if we subtract 5/6S from both sides, we get 1 whole minus 5/6 is 1/6 on the left, which is exactly conveniently what we needed. On the right-hand side, when you subtract, all the coefficients are 1. When subtracting here vertically, we get 1 minus 0. 2 copies of 5/6 minus 1 is 1 copy of 5/6. 3 copies of 5/6 squared minus 2 copies of 5/6 squared. Again, 3 minus 2 is 1. 4 minus 3 is 1. So this technique converts all the coefficients to 1, and we have a geometric situation. And the sum is the first term of 1 minus r. It's 1 over 1 minus 5/6, which is 1 over 1/6, or 6. And that should make sense. We expect 6 rolls until the first 2. Since the probability of getting a 2 is 1 out of 6, we expect that it will take the reciprocal 6 chances to get the first 2. Now, what if we have the same situation, but we assume that all the rolls before the first 2 are even? So it's a little bit subtle here. We're assuming all the rolls before the first 2 were even. So we want the expected value for the number of rolls it takes to reach a 2, given that all the previous rolls were even. It's a little bit subtle there. That last roll could be anything. So if you want to get the actual 2, that probability, whenever that happens in the string, it's 1/6. Now, in all the other cases, we know that those rolls are even. So in order to keep playing, you have to have missed the 2, and there's 2 out of 3 ways to do that. You can get the 4 or the 6. So that's where the 2/3 comes from. Factoring out 1/6, again, we have that same type of nearly geometric series. Again, I'm letting t be the inner bracket there. We're going to subtract r times t, 2/3 t on both sides. And again, when we subtract, we're going to get 1/3 t on the left. The right-hand side is the geometric series here. Let me just fill that in. Yeah, so filling in that missing piece there, if we multiply t by 2/3 and then do the subtraction, on the left we'll get 1/3 t. On the right, all the coefficients are 1, and we have the geometric series pattern. The ratio is less than 1 in absolute value. It will converge to 1 over 1 minus r, which is 2/3. So it's 1 over 1 minus 2/3, which is 1 over 1/3, or 3. Now, again, we have to get that original format there. We let t be the inside here. So there's still the 1/6 that we need. We need 1/6 t. We have a third t. So we have to multiply by a half here. Could also solve for t. T is 9 and then divide by 6. But we have a third t. Multiplying that by 1/2 will make it 1/6 t. And so the answer is 1/2 of 3, which is 3 over 2. The correct answer is actually what we call a geometric random variable, and the expected value is the reciprocal 1 over p. In this case here, p is actually 2/3. The first, the geometric random variable refers to first success happening on the nth trial. It's a little bit of a strange setup here. I leave this to something that you can discuss. But one way to get this probability is to look at it from the viewpoint that 2 and 4 are the bad rolls here, and the rest of the rolls, 1, 3, 5, and 6, are successes in some sense. And so that leaves you with the probability of success of 4 over 6, or 2/3, and then the 2/3 gets flipped over to 3 over 2. And a similar thing happened basically here. This was 1 over 1/6 to give us that 6 when there was no condition. When there was no condition there, probability of rolling a 2 is 1/6. The number of rolls to reach the first 2 is the reciprocal, which is 6. So I leave that for you to think about how we get this into the format where the probability of success here is 2/3. 1 over 2/3 flipped over does match the 3 halves that we found here. One other note here in this question, very important phrasing here, the rolls before the first 2 are even. So this keyword is before. We're not assuming that every roll is even. We're assuming all the rolls before the 2 appeared were even. All right, that wraps up lesson 27. If you have any questions, please don't hesitate to discuss or send an email. Thank you.